Hi, so we are Project Huayra, and this is our preliminary design presentation. Our team includes myself, Chloe McBride, Ryan Arnold, Heather Humphreys, Anthony Bianchi, Ashley Villa, and Dylan Bencher. The purpose of our project is to create a working engine model that can be used as a propulsion demonstration and test unit so that students are able to see various measurements and calculations in real time based on the theories and equations that they've learned primarily in their junior and senior level classes. There currently is no working engine model in the propulsion lab, so we want to be able to remedy this. First off, what are we building? We are building a turbojet, which is an air-breathing Brayton cycle engine that is used to produce thrust. It uses hot, high-pressure gases to spin a turbine, which in turn drives a compressor. A Brayton cycle is shown here in this diagram, where you have air coming into the compressor, going to a combustor where fuel is later added. Those are burned together, go to a turbine, and that eventually exits out typically through a nozzle. The picture on the other side of this slide here is a gas turbine engine. This particular one is actually used to generate power rather than thrust, but it is a very good example of a Brayton cycle where you have air coming in here, going through the various stages, and eventually exiting out that nozzle. Our overall system design is to have our inlet here at the front of the turbocharger. It will connect directly to the turbocharger inlet. The piping will then come from that turbocharger around and through the combustor here. That will then go to the turbine side of the turbocharger and eventually exit out the nozzle at the back. While all of this is happening, we have our oil system coming from the bottom here up to the turbocharger where it's cooling and lubricating the bearings. Our system goals are to have a compressor pressure ratio of 3:1 and produce 15 pounds of thrust while also sustaining combustion for 3 minutes. These values are derated some from what we calculated as our typical or ideal values, primarily to allow for a bit of a margin of safety in our design. Our deliverables for the preliminary design semester were to have a simulation of our instrumentation design, partial safety and operation manuals, and completed CAD for all of our components and an assembly. During our detailed design semester, we will be completing our prototype and instrumentation, as well as finishing our graphical user interface to be able to operate the machine, or the assembly, and complete our safety and operation manuals. We are moving on to component design. At the beginning of every component design section, we do have the part that we're talking about highlighted in gray here. So in this case, it will be the inlet and the nozzle. We are using a bell mouth inlet to capture and direct mass flow into the compressor side of the turbocharger. This will connect with a clamp directly to the turbocharger inlet, which governed the exit diameter of that inlet to be just over 4 inches. The entrance area required to capture the mass flow is calculated, and an entrance diameter was extracted from that, shown here in this table as a little under 9 inches. A bell mouth inlet is so named because it looks like a bell. It goes from a wider diameter to a narrower diameter before it connects to whatever it is used for. We will also be using a conversion-only nozzle at the exhaust of the turbojet. It will be connected to a pipe, which is also connected to the turbine side of the turbocharger. This is used to route hot exhaust gases from the turbine side of the turbocharger, and it will accelerate the flow to sonic before allowing it to exit the system. For this design, we calculated the area required to choke as being a little under 3 inches. A nozzle exit diameter was calculated from there, and the inlet diameter was governed by the pipe size of the system. I will now pass it off to Ryan to talk about the turbocharger.
Thank you, Chloe. The turbocharger that the team has chosen is a Garrett GT3782 VA turbocharger from a Ford F-250 Super Duty diesel truck. This turbocharger was selected for a couple of main reasons. One, since it comes from a Ford truck, it's common and there's lots of information on it. And two, the size. It's small. It's small enough that the thrust that's projected to come from it is easy to manage, and also it's not super heavy and cumbersome, but it's also large enough that mounting sensors is not a super huge deal. Some of the information that we found for this turbo is a compressor and turbine map, which with the help of PCA or parametric cycle analysis made choosing a design point very easy. This design point is a stage pressure ratio of 3 to 1, an isentropic efficiency of the compressor of 75%, and an isentropic efficiency of the turbine of 70%, all spinning at 110,000 RPM. This turbocharger uses centrifugal turbo machinery due to the fact that at low corrected mass flow rates at the inlet of around 5 pound mass per second or less, a centrifugal system will surpass an axial system in terms of isentropic efficiency, making it favorable. This is because at these flow rates, an axial system has short blade heights, and the aero profile of these blades will become dominated by tip clearance vortices that make the isentropic efficiency of the entire compressor drop significantly. Due to the fact that mass flow rate with the centrifugal system scales with radius, not blade height, since they don't have blades, they have vanes, that they're not plagued by that problem. They also exhibit extremely high stage pressure rises, in some cases as high as 3, 4, or even 5 to 1, versus on axial systems 1.4 to 1 as a ballpark area. This particular turbocharger also has a neat feature called variable geometry turbine stator vanes that change their geometry with respect to mass flow rate. Shown here in this photo, when the mass flow rate is low, such as when the engine is being spun up and started, the vanes will tighten up, the float area will decrease, and the impingement angle onto the rotor is increased, which increases the specific work output. As you can see, these vanes have a low flow area there. And then as the engine speeds up, the vanes will open up again, the float area will increase, the impingement angle is dropped, and since the flow rate is higher, that flow speed is maintained, and the end result of all this is a relatively constant work output from the turbine across a wide band of operation. Shown here is a basic cutaway of a turbo. Air is brought in through station 1, the inlet where it is introduced to station 2, the compressor rotor by the front vanes here, which is called the inducer. That air is grabbed by these four forward swept vanes, which are spin clockwise in this example, where the rotor imparts rotational energy on to the working fluid, air, and that is slung radially outward, where it is captured by station 3, the scroll. That scroll would typically send that flow to the inlet of an IC engine for an automotive application. In this case, that is going straight to the inlet of the combustor assembly. Station 4, shown here, my laser pointers, there it goes right there. Station 4 is the bearing housing. This houses radial and thrust bearings that keep the position of both rotors constrained and do away with wear. these are spinning super fast, right? So the laser's not working, sorry. So these are spinning super fast. So if they weren't cooled, then they would overheat and break down. So to manage this problem, cooling oil is flown through the top flange on top, where it circulates through the housing and the bearings, and then it is sent out the bottom flange there. At this point, there is hot combustion gases that have exited the combustor, and those are channeled into station 5, the turbine scroll, where they're sped up and then flown through those veins that we spoke about earlier, and then that is impinged onto station 6. There it goes. The turbine rotor that expands that air to a lower pressure and uses that work to drive the compressor, which completes the cycle. From there, that gas is sent out the back and then throttled to a sonic condition through the nozzle at station 7. I'm not going to hand it off to Heather Humphreys, who's going to talk about the combustor and fuel injection systems.
Thank you, Ryan. So first, this table is a list of our major combustor design requirements. Some of the most important ones folded here on the table are comprised of the fuel-to-air ratio of 0.0176, the combustor operation temperature of 1340 degrees Fahrenheit, and the film type of cooling in which bypass air flows through the flame tube in order to cool the combustor. The following picture is an overall assembly view, an exploded view of our combustor design. We're broken into 4 major components: the conical diffuser, the dump diffuser, the flame tube, as well as the casing. The assembly is 21 inches overall in length. The first stage of the combustor is the dual section conical diffuser with a 9-degree double angle. The piping begins at 2 inches in diameter and increases to 4 inches with a 5-inch overall length. This component is constructed of carbon steel, and it is designed to minimize pressure losses both due to diffusion and friction. The second stage of the combustor is the dump diffuser. This is designed to conserve both length and weight. The piping begins at 4 inches and increases to 6 inches in diameter with an overall length of 4 inches. This component is also constructed of carbon steel. It's an easily manufactured component with a projected inlet tube that is designed to encourage stable diffusion. The inlet of the dump diffuser does mate to the exducer of the conical diffuser at a 60-degree angle. The flame tube and casing assembly is designed in a tubular style with a 6-inch diameter casing and a 4-inch diameter flame tube. There is a 3D printed version of this over on the table here. There are braces in between the flame tube and the casing. These are designed to increase the alignment. The swirler and impinging jets create a toroidal recirculation zone. The swirler number has a value of 2, which is above the critical value of 0.6. The presence of the gradual dilution cooling flow does eliminate the dilution zone. Shown at the bottom of the slide here is a cross-section cut of the full assembly stacked together. The flame tube and casing assembly are both constructed of stainless steel 304 piping. This was selected due to the high temperature tolerance limit of 1500 degrees Fahrenheit. The dump diffuser and flanges, on the other hand, are constructed of carbon steel. This is because they are not directly exposed to high temperature flame, and cooling air does pass over these components. We will now talk about the fuel injection design. The first step in deciding on the fuel injection design was deciding the type of fuel to be used. In this, I compared 2 different types of fuel, liquid diesel fuel and gaseous propane fuel. using 5 rank criteria: ease of ignition, cost, accessibility, ease of implementation, and available resources. On all criteria, except one where it tied with liquid diesel fuel, gaseous propane fuel did rank higher, giving it a higher overall ranking of 4.55 as opposed to 2.7 for diesel fuel. This made this the best choice for our design. In terms of accessibility, they did tie. We're able to get either of these fuels pretty well. So in order to inject our propane fuel, we decided to go with a fuel injection ring style. The fuel flow through all the holes in the ring is going to be governed by the upstream pressure as well as the hole diameter. The ring will have an overall diameter of about 1.5 inches, and the holes will have about 3/4 millimeter diameter. A total of 8 holes gives us our desired gas flow rate. In terms of placement for the fuel injection ring, it will be centered in the combustor inlet, and the diameter of approximately 1.5 inches lines up to where it will be aligned with the airflow path. The holes will be oriented nearly perpendicular to the incoming airflow, and this promotes the mixing and gives us our desired fuel-to-air ratio. In terms of ignition, we'll be using a standard diesel spark plug. This spark plug will be positioned opposite of air entry into the combustor and not centrally placed, and this will allow ample time for both the fuel and air to mix before ignition. And I will now pass it off to Tony to talk about the plumbing and oil systems.
Thank you, Heather. So the primary purpose of the plumbing system for Project Huayra is to integrate the individual components that we'll be using and provide a proper flow path for all the working fluids in the system. As you can see here, we'll be using 2-inch piping for the cold air section, connecting between the exit of the compressor and the inlet of the combustor. We'll also be using 1/2 inch flexible tubing for the oil system seen here, and 3/4 inch flexible tubing used for the fuel system. In the plumbing system, we'll be using 3 main types of integration. The first of which being a flexible silicone rubber tubing with adjustable hose clamp seen here in the bottom left. This type of integration is commonly used for cold flow sections of piping and also allows a degree of flexibility in the system. We will be using this type of integration for the exit of the compressor, going towards the 2-inch tubing that leads to the combustor. The next type of integration we'll be using is a V-band flange with a clamp shown here in the middle. The V-band flange is very common, can be seen often in exhaust systems and automotive applications. We will be using this V-band flange to connect the exit of the combustor to the inlet of the turbine. The last type of integration we'll be using is a common 8-bolt flange connection that can be seen here in the bottom right. We'll be using both these 8-bolt flanges on the inlet side of the combustor, as Heather mentioned. So for the oil system, as stated before, the purpose of the oil system is to cool and lubricate the turbo bearings. As you can see by the flow diagram here, the oil will begin in the tank, then be passed to the oil pump, where it will then be pumped through the oil filter and up to the top of the turbo bearing housing. Here, the oil will flow over the turbo bearings, properly lubricating them and taking away heat, where the oil will then flow back to the tank and the cycle will start again. As you can see, this is a recirculating system, so once the oil reaches the tank, the process restarts and the oil is reused. For our oil system, we already have the main components selected. The first of which being a 3-gallon vented oil tank. We've chosen a vented oil tank to have an open system, which allows all of the work put into the system by the pump to go into flow rate of the oil rather than pressurizing the system. This is important for our design because we want the most amount of oil flowing over the turbo bearings in order to ensure that they do not wear prematurely. This specific tank also has a temperature gauge on the outside, which allows us to monitor the temperature of the oil in the system. The next component selected is a 3.7 gallon per minute geared oil pump. We've chosen this flow rate because our oil system is very closely related to automotive applications that use 3 to 4 gallon per minute pumps. We've chosen a geared oil pump because the internal components are made of brass gears rather than plastic components, which can withstand the temperatures around 250 degrees Fahrenheit that we're expecting to see in our system. The last selected component is an inline oil filter, very similar to one you would see in an engine of a car. We've chosen this because they can withstand the temperature we're expecting to see in the system and also are very easily sourced. Again, the primary purpose of the oil filter is so that the cleanest oil is flowing to the turbo bearings to prevent buildup of particles. As for the oil in the system, we will be using a 0W30 full synthetic motor oil. We've chosen this weight because it has a low viscosity at lower temperatures. For example, startup of our system. It's important because we want the oil still flowing over the turbo bearing, because startup is when most of the wear happens in the system. Full synthetic also will perform better at the design temperature that we've chosen and resist coking or breakdown a lot better than organic fuels will. There's also, with full synthetic, there's also less severe solid carbon deposit buildup over the operational life of the system. I'll now pass it off to Ashley to talk about data acquisition.
Thank you, Tony. So as Tony said, I will be going through the data acquisition for the system. So this is an overall, very brief diagram of what the system looks like. We'll be taking temperature and pressure measurements in 4 places. First at the inlet, between the compressor and combustor, between the combustor and the turbine, and then finally at the nozzle. These different measurements will be used so that we can calculate and verify thrust, compressor pressure ratio, thermal efficiency, and combustor temperature. Another design that we would like to implement is being able to measure RPM. However, we're still looking into the possibilities of doing that. So this is the microcontroller that all of the instrumentation will be connected to. It has a power rail that can directly power all of our instrumentation, which makes it pretty useful. We chose the C2000 Piccolo Launchpad from Texas Instruments. It has 21 analog to digital converters. We're only taking measurements in 4 places, so this is a little bit more than we need. However, it's better to have more than less in case we have time to continue taking measurements in places we didn't anticipate at the beginning. The microcontroller can be programmed using a MATLAB to C compiler or even Simulink. Simulink is better for parallel coding, however, we would prefer to do sequential because it's a little bit easier. The microcontroller, the ADCs can gather data at 3.45 million samples per second, which is very, very fast. We don't need that for our project necessarily, but if we wanted to, it's good to have that type of capability. For 3 minutes of duration, we could probably sample slower, which is why we would like to leverage some of the other capabilities on there, such as the timers that are built into the microcontroller. Other features within the controller are motor applications, as well as pulse width modulation, which we could utilize if we feel the need to. This is an overall flow diagram of not only how the instrumentation and data acquisition will work, but also another one for the code sequence. So up here we show that the instrumentation is going to emit a voltage that connects directly to the microcontroller's ADCs. This will connect directly to a PC or laptop via USB. The USB will not only be the thing that helps the PC program the microcontroller, but it also makes it so we can gather data directly from the PC in real time. MATLAB code will be running on the PC or laptop, and upon code completion, an Excel spreadsheet will be given back to us so that the student or teacher using this will be able to have real-time data that was gathered while the system was running that they could do for further analysis or demonstration. Here we have the code sequence. Up here, MATLAB saves all of the variables that were gathered from the instrumentation into a structure. The structure is divided into 2 parts, the first being the parameter type and the second being the location in the system. That is so that when we look at the data later, it's not just a number, it's a number with a name. This will allow us to not be able to identify when there's a problem later where that is and what type of issue it is, whether it's a pressure and temperature for the parameter type, and location could be the inlet, the nozzle, or anywhere else in the system. Every single parameter that is gathered will be put through a safety function that we created ourselves. This safety function will make sure that it's not above a rated value, and it will also ensure that if it's within a certain safety margin, we'll be able to identify that while it's running. Most likely, we will never actually have to use the safety function, but it's good to have it just in case. Afterwards, if a warning needs to occur, it'll give the user a notification, whether it's within that safety margin or whether it's within an area where we should be checking the system. Otherwise, it'll go to a GUI display or graphical user interface. This will be showing all the data as it's gathered in real time, and that way the student or teacher can monitor the system as well as be able to analyze the data while being able to view it. And then finally, it'll give us the Excel spreadsheet at the end. So this is the current running simulation that we have for the graphical user interface. Right now, it's animating a sine or cosine waveform, as you can see. It does it against time, and this is running like as soon as you press start, it'll keep going until you tell it to stop. I've tested it for short and long durations of time to make sure that it's actually accurate, and it appears to be that way. The sine and cosine waves are not actually important. These will ultimately be replaced with pressure or temperature curves so that we can monitor the system, as I said before, in different areas. Right now it's a drop-down menu, so you can pick between what type of curve you're seeing. However, I could eventually, which I have tested, is make it so that you can see all the curves at once. Lastly, there is the stop button, and so that once the system is completed running, you can tell it to stop whenever you're ready, or if you only wanted to run for a couple minutes rather than the entire 3-minute duration. There's also an amplitude value. This is static text currently. However, eventually this will be changed into the most current value seen on your graph. So that way you'll be able to see what's most up to date. So this is the safety function that I mentioned before. It's user defined. This is the parameter or value that will be going in. This is a rating and safety margin that is up to our discretion. The safety margin is something that will allow us to make sure that we're anywhere near the rating. We can let the user know using this warning. And then if it's near, like perfectly onto the rating, it'll give us this error. The parameter type and location are just so that when the user gets the notification, they will be able to see where it is and what type of parameter they're looking at, rather than having to guess where it is and figure out which ADC it's connected to. They'll just be notified. So some of the unique things are that this can run in real time between the microcontroller as well as MATLAB. This is unique because MATLAB is typically known for being slow. However, we're also slowing down the microcontroller because very fast data is not necessarily needed for our applications, but we do need data so that we can be able to monitor the system. And because it's a test demonstration, it'll be something that the students can use in general. So it doesn't have to be exactly exact in terms of timing, but it can be something that they can use. Interrupts are also something that we're using. Interrupts within MATLAB are a little bit faster for optimizing the code so that if a user input is put into the MATLAB GUI, it'll respond more quickly than if we just use regular user functionality. User functionality only works in sequential coding, but interrupts will allow it to jump back and forth between different functions. The main purpose of the data acquisition is not only to verify the system, but also be able to monitor it. It's entirely for demonstration purposes, so I think data acquisition is incredibly unique for our project. And the fact that we can save it for later is very useful for students that want to do some sort of calculation or process using data that was actually required. I'll now pass it off to Dylan for test stand and safety.
Thank you, Ashley. So our test stand is going to be divided into two horizontal parts. The first part, the top section, is going to contain the turbo, the combustor, and the nozzle, while the bottom section is going to contain the propane fuel source, the oil system, and all underlying electrical components. The proposed dimensions for our test stand are 56 inches high, 42¼ inches wide, and 27 inches deep. When selecting material for our test stand, we were originally planning on using carbon steel for its rigidity and ease of manufacture. Upon further investigation, we were able to scrounge material off of a previous capstone project. This material was a T-slotted 6105 T5 aluminum Series 40. This is produced by the company 8020 and it's used for many test stands. It's very unique in this T-slide profile here. This allows us to cinch down onto the components individually and make sure that vibrations that we are expecting are ceased. The proposed strength, or the yield strength, excuse me, of the bars themselves are 35 KSI per bar. For the individual component mounting, we are going to mount each component if we're expecting high temperatures on the cold side, such as the combustor. We will mount it onto the dump diffuser. We will do this by cinching onto this ring right here and then mounting it to the test stand. We have also acquired a pedestal for the turbo. The turbo will be mounted to the turbo pedestal and then subsequently mounted to the test stand. Also, instrumentation will be mounted to the individual components and then mounted onto the test stand to secure them and make sure they do not fall off. For safety, on 3 sides of the top section, we will have impact-resistant safety glass. This is plexiglass that is 1/4 inch thick. This is to prevent the worst-case scenario and protect the users in case the turbo housing fails. We also are within ASME standards by isolating our fuel source from the flame source in the combustor. We are doing this by 2 degrees of separation. One is the vertical separation by keeping the fuel source down on the bottom section, having the crossbars, and then having the combustor on the top section. For OSHA, we will follow all propane safety by storing it away from the combustor and also mounting it onto this base right here. We have also been gathering material data safety sheets for our propane and oil source per OSHA safety standards. Additionally, we have begun acquiring the operational safety manual. The safety manual will tell the users how to safely turn on, turn off the engine, and what to do in case of emergency. On the fuel line, we will have 3 valves to control the fuel source. The first valve is going to be the standard tank regulation valve that will be included on the 5-gallon propane tank. We will use this valve to control how much fuel is actually going to the combustor. Later on, we will have a reverse flow valve. This valve is requested by ASME to ensure that the flame from the combustor does not go back into the fuel source. Finally, we'll have an exterior shock valve mounted on the outside of the test stand for worst case scenario situations and also to just turn off the engine. I'll now hand off to Chloe to talk about budget and labor.
Thank you, Dylan. So we started off the semester with a $900 budget. We have so far purchased our turbocharger and parts of the electrical system and the test stand. In the earlier part of next semester, we will be purchasing the rest of our parts as well as any raw materials that we will need for manufacturing. Our actual versus projected labor hours, we were able to stay pretty close to our projected. We had a couple of weeks in November where some tasks took longer than we anticipated, so we went a little bit higher then. But we were able to stay within a pretty close margin of our projected. The projected were based on each team member putting in 12 hours of work outside of class per week, which gave us about 1,080 projected, and we ended up at just over 1,100 as our actual total. Broken up by category, we had about 460 hours on administrative, presentation, report-related items, and the rest being a little over 640 put into engineering hours. Next discuss what we have accomplished and what our next steps are. This semester, we were able to complete our CAD assembly and all of our CAD for components. We also have an instrumentation simulation and have done some code testing. We have partial safety and operation manuals and have purchased some of our parts. Our next steps will be to continue purchasing parts and begin manufacturing others. Once that is complete, we will be able to build our system and begin testing. By the end of next semester, we will also have our completed safety and operation manuals. We'd like to acknowledge several people. There have been a lot of professors who have helped us with questions over the course of this semester. We've also had several companies who have either donated items or given us significant discounts on those, and these are all listed here. So thank you to everyone. Thank you for listening, and are there any questions?
Are you guys planning to put any protection in place in front of the inlet for the turbo pump? Any sort of like mesh shield or something to prevent, fog or anything from getting in and damaging any of the components or fingers or small children or anything like that?
We haven't looked super closely into it yet, but it's been considered.
Okay, yeah, that would be a really good addition as part of that. I was really impressed, by the way, with the mention toward the end of the ASME and OSHA standard stuff. I think that was really good to kind of consider that. I think a lot of teams overlook a lot of those standards and kind of the best practices for looking at their design, so I was really impressed with that. Kind of small thing, 24 units. If you open the presentation, by the way, you can just type in 24.
I tried that and it didn't work.
Oh, really? Oh,
Yeah.
I apologize then. Units, there's kind of back and forth. I realize propulsion's kind of in the weird fuzzy area. We really like our conventional units, but having both metric and non on the same slide was it's hard for me to kind of judge in comparison between those. So having some consistency, I guess, across the board either way would have been a lot better. Let's see, what are some of the other things here? Overall, it was really good. You answered a lot of my questions later on. Really quickly, maybe I just don't understand. How is you talked a lot about the data acquisition system and the electronics running that, but actually starting and ignition of the turbo pump and the kind of maintenance of that element of it, that's not done through your system, right? There's an auxiliary system for that?
There will be. We've been going back and forth between a couple of options on how exactly we want to do that.
Okay.
And a little bit of that may just come from what turns out to be the best option as we start building it next semester. We consider starting it with essentially a drill, getting it up to a high RPM, and we've also considered starting it with a high flow rate from a blower.
Okay. The data acquisition side, getting the data in real time, that's not controlling any of that in any way, right? So what is the control mechanism to say, hey, we're having a problem, we have this great warning come up in our GUI, that's nice, but how do we turn that into we're going to shut the thing down now?
So the easiest way to shut down the engine, no matter what is happening, is that exterior flow valve. That is just going to basically choke all the flow of the propane to the combustor, which will just shut down the engine. If anything goes wrong, that's the go-to.
Okay, so you always have, has there been kind of like a con-ops or like a plan of operations on how you're going to have people initiated during the test and who's going to be controlling?
That's going to be in that safety manual that we're producing right now.
Okay, so it's in process.
Yes.
Okay, so the safety element, of course, with any of these things is really valid. And so kind of bringing some more of that to the forefront in a presentation like this, I would enjoy. Thank you.
Good job, guys. The first question is kind of a two-parter starting on 12. So, I would have liked to see a little bit more about this, but did you just basically walk me through the selection process for, did you look at any other turbos or anything like that? This is just what was available.
So we did look at other options. There were two in our school as is. One was used as an afterburn burn project a while back, and the turbine was put bluntly eaten alive by that flow, and it was chipped and warped, and it was not good. So we chose that one. While it was big and super cool, wouldn't be a great option. The other one was quite small, so mounting sensors and whatnot on that is harder, and also there was almost no documentation for it. So things like the compressor map, we couldn't find, and that's a very important piece of the puzzle that we need to properly analyze it. So we chose to find one that had that information, and that info made our lives like way easier.
Okay, so the second part is, so you got turbo selection, so how are the temperatures that you're gonna be operating this compared to what that turbo was designed to operate at?
And so that was actually one of the pieces of info as well. The rotor's made of a nickel-based super alloy that the manufacturer won't say what's in it, but it is rated for 50 degrees C, which is under the design limit. And that's under its yield strength at that temperature as well.
Okay. Very good. So slide 31. So it's good that, because I had a question, you had the oil system on before, and the first question was how you're gonna cool it, but then you kind of addressed that, but with your temperature limits. So it turns out, so it doesn't seem like you thought that there's very high chance that you could go above your temperature limits, but you got a temperature, yeah, which is good, but if it turns out that you do end up needing more oil cooling, what's your path forward? Have you thought about that?
We have thought about what options could be done, and in cases of us exceeding the expected temperature, we could look at like external oil coolers that pass either heat exchanger, so it's passing water through and dissipating the heat, or like an electric fan or something to cool the oil. Currently, since our oil system was very closely designed to an automotive oil system, we don't expect it to, but in the case that we do need to cool the oil more, there are some options that we could look at.
My last question is, so, Cameron, so go to slide 38, and this is kind of tied to the safety part too. So you mentioned your manual shut off, and the warning tells me that temperature is exceeding what it was rated to check the system. I feel like that's a pretty serious condition, and I wanted to know if you looked into any sort of way you can do like an electronic shutdown. So then you have your physical valve, and you can, I don't know how you can route that as far as you need to, but it seems like you kind of want some way to electronically shut down. But
We have investigated it, but we're just not quite sure whether we need that yet or not, and whenever we cross that bridge.
I think it's just because I'm scared of jet engines, but I don't want to be in like another room and have this going on somewhere else, but I'm sure you'll get.
Yeah, we have discussed it, and we have a couple ideas in the mix about how we're going to do it, just not final say yet.
Okay, nice job.
It's my turn. Excellent, very nice job. So, chart 5, the 6.
Slide 6.
I'm just not understanding, but do you have the goal and typical conversation?
No, the typical is essentially what we calculated as this is theoretically possible. The likelihood of that happening is relatively low, so we limited this up.
Ideal would be better.
Yeah.
Typical or ideal, yeah, that's why I said it as typical or ideal, we have the column as typical. Yeah.
And then slide 9 and 10. How are you intending to fabricate these parts?
These are most likely going to have to be CNC'd out. There may not really be any other way to do it. This one is going to be, actually this one can likely be 3D printed because it doesn't have hardly any temperatures, any high temperature going to it. It's taking in ambient air, it's going to the compressor side of the turbocharger. So there shouldn't be any high temperatures that would cause it to melt.
Careful where it's mounted. But
Yeah. And we are looking a little bit closer into that. That's why I say this will likely be able to be 3D printed. We just need to double check some of the temperatures at the very front of the turbocharger. And then the nozzle is very short, so it would really only need a small piece of steel. And then this flange will also be separate from it, so it can just be welded together rather than CNC'd or manufactured as a single component.
just in welding is not always a good
Not necessarily, it's basically just to halt some of the flow. It's not an
On
absolute
the
essential.
outside,
On the outside?
like this is got.
Oh, okay. It could probably be removed.
So, is there any concern with the outside surface temperature of the combustor? I know you got the safety thing, so that is your protection, is the plexiglass on the outside, so no one's gonna get dirty in.
Yes.
Oh, on the, chart 29. Can you explain why you chose, particularly the V-clamp one, why not just a bolted flange for that joint?
Yeah, so the inlet to the turbine side, the turbo that you can see here, actually already has half of the flange. So we manufactured, or we will be manufacturing the other half.
That's all I have, thank you.
Okay, so I have a question about the Belknap inlet as well. Are you guys planning on using that to measure the mass flow rate through the engine?
No. We have the compressor map, so we know based on the pressure what the flow rate is.
Okay. Let's see. Next thing I had was. All right. So for your fuel injector ring. All right. So how are you going to ensure that the fuel flow is even through all of those holes? That was a problem that popped up last year.
That's something we've actually thought of recently. Next semester, we plan to do a lot of experimentation, see if we can maybe test how well the fuel and air is mixing further on down past the injection ring. So that's
Well, what I mean is the amount of fuel that's coming out each of the holes.
right. That's something we've considered, but we're still kind of in the works on thinking about.
Okay, so it's still to be addressed.
Yes.
Okay. So my next question was, what does the mixing look like based on that configuration, and how are you going to know if it's adequate?
That's something still
You're gonna-
to be determined, yes.
Okay, that's going to be addressed next semester, I
Yes.
guess? Okay. So make sure you address it next semester. All right, so oil tank, I guess we're all going to hit on the oil tank. Do you guys have an estimate on what the temperature rise for that's going to be for your test duration? Because you're saying that you think it's adequate to cool the way it is. How do you know that?
We haven't done any analysis on the temperature rise from room temperature as the system starts up. Again, we're just basing it off of automotive. They don't often exceed the temperatures over their duration, so we do have a shorter duration of around 3 minutes. I guess we're going to watch the temperature and make sure it doesn't.
Okay, when you have a 3-gallon tank, are you going to use 3 gallons?
Yeah, with the pump we're using, it will flow through quite a bit. We won't be filling the tank all the way. We want a decent space for the tank. We don't obviously want to overflow the tank, but yes.
So you don't know how much energy it would take to heat up the 3 gallons to above your unspecified criteria for oil tank?
I don't believe that would be too difficult, but we haven't looked into it yet.
That brings me to, what is your oil tank criteria?
Criteria is in,
How do you know it's too hot? Not like you're going to measure using the thermometer, right?
yeah.
But what level on the thermometer tells you that the oil is too hot? The top. Okay, so
Yeah.
question answered.
Yeah, we're just planning on monitoring the oil temp in the system as we run it. And if it starts getting past the range of 250 degrees, then we would shut down the system.
So 250 is the.
Yeah.
Okay, that was what I was asking.
Okay, yeah.
Okay. Then for data acquisition and measurement stuff, do you have the sensors that you're planning on using? The probes, the things? got a list of, yeah, there we go, slide 34. You got all those pressures and temperatures. How are you going to measure something like P9 or T4?
We know basically what we're using and have a couple of models considered. We have not actually acquired the instrumentation yet.
Okay, are you planning on using,
Yes, we were planning on talking to you
does the
about it.
person who's in charge of those know this? Thinking that they don't. All right, what are the expected values of all these?
I'm not telling you those off the top of my head.
So there's lots of those, right? There's in the backup slides a screenshot of the PCA done on them, and if you want them, then we can show those now.
Yeah, but it's not a screenshot of the entire thing, but it is.
I made a spreadsheet that's adaptive, that changes with inputs such as flow.
Yeah. So when you come to see me about getting the sensors, I'm going to want to see what you expect the values for each of those measurements to be.
Yeah, of course, it's fine.
Let's see. Okay, I think I'm down to just two more things. One is the test frame. Dylan, you had mentioned that you were using the 80/20 aluminum, and it was going to be adequately stiff.
Yes. So this L bracket, which is shown in that middle picture there, the angle of twist is to 2 degrees. We're not expecting the vibration to cause any twist, and the only thing that we should be worried about is the yielding strength, which we're nowhere near reaching our max for the 80/20 and the L brackets combined.
Right. So, I mean, my question is that I've seen this put together and you can shake it. So, how are you going to ensure that that's not happening?
The entire test stand frame. Well, originally we were planning on putting in casters for next semester, so that's something that we'll have to.
All right, we'll have to talk about that. Anyway, and then the last thing is that we need to definitely meet about safety and having fire in the propulsion lab. So, we need to talk about that. All right. Well, good job, guys. That was I really like the design, so good job.
Well, back to the oil tank. I'm just wondering, budget, couldn't you just put a temperature sensor in an oil tank and run it to your buoy? And it would come up right in front and say, okay,
Yeah, we thought about that. We found a tank that has the thermometer on the outside. It's not the most ideal, but we have thought about just putting a thermocouple straight into the oil so we can measure the temperature.
I'm just gonna spit these out and know. Your I/O board, your data, is it, the inputs on it, are they configurable to different types of input signals? Are you gonna get stuck there with, it doesn't accept 120 or it doesn't accept millivolts, whatever comes out of your sensors?
So from my understanding, it seems like the board is rated to read anywhere from 0 to 5 volts. If I find that there's an issue, I would just hook up an external way of reading it. It's not ideal, but it is a way of reading it. It goes into the board.
So this convert milliamps to. I was kind of wondering, just myself, when you talked about the stand, are you going to tie it to the floor while you're running the engine, or is it going to be enough thrust to actually take it over?
No, like we had on an earlier slide, we're only expecting about 15 pounds of thrust. I did the equations for it, and with the amount of weight that we have in the bottom, additionally with the turbo, there's really no way it's going to fall.
And I think you mentioned exhaust routing already, so I'll skip that. I like your comment that you're looking at being able to overlay excuse me, in 5 minutes or someone say, well, can you plot this one and this one simultaneously so I can see what's going on? So I like that you're doing it. That's it for me. Good job.
Are you gonna run it without nozzle for the initial shakedowns to cut down the back pressure?
Probably.
Your efficiencies are low on your compressor and turbine. How sensitive are you that if this is not the optimum casting, that if you're a couple points low on efficiency, this thing will never run? Have you figured out a sensitivity of how much margin you got?
You are right. The answer is that it is very sensitive. I've calculated it in that spreadsheet, all of what I expect at our atmosphere here and everything else. So I've accounted for everything I could possibly imagine. But the answer is that we're teetering on that line.
Okay.
So that's a problem that we'll face head on the moment it happens. Sadly, there's not much that we can do to avoid that.
Are you controlling the variable geometry on the turbine through a factory component or through your lab view, or what's the scheme there?
Yeah, so there's a solenoid on the turbo that came from Ford. It's hydraulic, so when it actuates, it moves the oil inside of there, and then it spins a cam lobe, which I can actually point out right here. There's a cam lobe that mounts from there, and then this will spin like that.
Okay.
And that'll open and close those, and we can, in theory, control that from our board as well.
In the combustor section, you mentioned a diesel spark plug. Diesels don't have spark plugs.
Not a diesel spark plug.
No, diesel, sorry, I misspoke.
So be careful what you say. Are you gonna spark it like 10 times and then turn it off, or are you gonna be sparking the whole 3 minutes? Because, jet engine doesn't need it all the time, but I didn't know what your scheme was.
The idea is to spark it until it's lit and we know it's stable, and then once it's on, stop.
When it's,
Yeah.
with the KISS principle, you just run it all the time. I mean, early engines, some of them, that's what they did.
Yeah.
It's just easier. RPM, you said you weren't sure whether you were doing RPM. RPM is super important in starting, because when it doesn't start, you won't know, do we not have enough RPM? I mean, you get some off the pressure rise on the map, but you're gonna be doing something weird. It could either a leaf blower or whatever. Your compressor map may not be what you think the compressor map is, because it's not running under its own oomph, technical term, okay? And so you wanna know what the RPM is.
That's true, yeah.
I think those were my biggies. All right, nice job.
Thank you.
So the reason I said maybe isn't because I don't think we can. So right now we're looking into using a magnet that has a wire coiled around it, and it'll essentially, every time the blade passes, it'll produce a magnetic field. And using the microcontroller, which should be fast enough, we would be able to measure how much current is coming out, but because there are 13 blades on the turbine, it goes really fast, so the frequency is really high. I'm not sure, from a perspective that I know that the microcontroller can read it, I'm not 100% sure how it would read currents in the same way it does voltage. So there might be some converting that I have to do, or using some sort of resistor in the mix, and I'm looking into it still, so I know it's going to happen, I just haven't quite figured out how.
Keep pushing on that, because the rest of the team will want it.
Yeah.
It's very important.
Okay, it's a really exciting project. Hope it works. I would like to say to take a look at your thermodynamic properties, especially your exit pressure, total pressure, what the pressure losses you expect through the engine. You have a 3-to-1 pressure rise if you get it. That's at max RPM.
No, it's not. Well, it's not. The design point is underrated from its limit. The top end is about 3.7 to 1 actually.
Okay, Professor Mapp would be helpful.
It's in the backup slides.
Actually, yeah.
Okay, yeah, we don't know how much time we have, so,
Not much.
I may look at it later. Okay, so this picture right here, what are your swirl angles? What are your swirl angles?
The swirler angles, which we can show right here, are 70 degrees cut.
Okay. And they give you a swirl number, you said of two?
Yes.
And,
Two.
for on-axis recirculation, you have 0.6.
Mhm.
Where do you expect that flame to actually establish itself?
The flame should establish itself between, can you hold that? Thank you. It's going to establish itself between these holes here and the front face here, because this is where these holes will like impinge flow and recirculate here, so it'll be right around here.
Okay, so you don't have hardly any axial velocity in that recirculation zone.
Yes.
You have pretty good velocity in the opposite direction. You've got the spark plug in there, you've got your fuel injection system. You need a little bit of space so it doesn't burn up. I don't know where it's going to set up. A little bit with that those high of angles. You may be recirculating flame really close to that fuel injection system, and with gas, it's gonna light. So
I agree. The dimensions that we chose were all from multiple peer review
okay,
resources, so these are actually on the conservative size, but yes, it's a potential problem that.
from an angle standpoint, so you've
Yes.
seen bigger angles than
Yeah,
70 degrees.
they tested up to 80
Okay.
with a scroll number of around 4 at that point, yeah.
Okay. On your, I would like to see your Excel spreadsheet.
Oh, okay. Okay.
So, so you have 99 kilopascals at the nozzle. That's your total pressure? Okay.
That's your total temp there. The pressure is on.
Yeah, 99 kilopascals is your total pressure, right?
Yeah.
You're going down to 84.
Mhm.
What's the pressure ratio
From where?
from the nozzle exit total pressure? You got,
So if we go to the design points, yeah, there's, all right, well, either way, I try to account for losses throughout every step. If I remember correctly, the total pressure ratio across the nozzle is 0.95.
okay, yeah, but you've got the exhaust gas total temperature is 84 kilopascals.
Yes.
Okay, what's
So
that?
that's ambient, like atmospheric.
Okay, what's your total pressure?
The total pressure is that. So that last station, the exhaust is out like after it leaves and is a part of the atmospheric air at that point.
So how are you going to get Mach 1?
You taper the nozzle.
You need pressure. You need total pressure. You need a pressure difference that is, so your total pressure coming into that nozzle has to be over 1.8 times higher than your static pressure at the exit in absolute units in order to get Mach 1. So,
I can check my calcs. There could be an error. I tried to not have those, obviously, but
okay.
But we used NRP and the flow that we expect to find that sizing. But if it needs,
It's not a size issue, it's a pressure issue. So as I just want to make sure I understand, you've got conservative values for pressure loss. You don't have very much total pressure. You've got 3-to-1 pressure ratio if you can get it, okay? And then by the time you get through pressure losses due to your turbine efficiencies and your compressor efficiencies going through that turbine, do you have enough total pressure at the exit of that turbine to drive the flow to a velocity that's going to give you any thrust to get that out? And so that's you probably need to look at the description.
Of course.
Going back to units, units are a language in and of themselves. You've got SI units here, and you've got a multitude of other units. These are hopefully in Kelvin. You've got degrees C, you've got degrees F. So it becomes really, really, really difficult from a presentation standpoint to compare it. So you can pick the SI, but then use that throughout. You can put in parentheses what it would be inches, because sometimes things are purchased in inches.
Yeah, of course.
But just for consistency throughout.
That's my fault on that front. I use those, and then we found out that our audience would
I don't have a problem with
prefer
using those
standard
units.
ones.
It's just the consistency through the presentation. So when we are talking about temperature at the exit of the burner, at the combustor, what is the expected temperature, highest temperature that burner is going to see? What is it?
The flame temp?
Yes.
The flame temp is around 2,400 Fahrenheit, but the walls are filled cool too.
Okay, and then you said the material the steel that you're using has a max temperature of what?
1,500 degrees Fahrenheit.
1,500 degrees Fahrenheit. So those things, the connection between maximum temperatures and material temperatures, and then what you're going to do with those materials, really important as I think these things are talked about in different areas of the presentation, and so trying to put that information together is difficult for the audience. So just keep that in mind, especially as you're going forward, to make sure you've got the information that you need to make decisions. Okay, well, good job. It's a challenging project, a lot of stuff going on, a lot of disciplines. One more question. Instrumentation, filtering. Can you filter data with the board that you're using?
So technically no, but the way I was going to do it was just after each of the inputs are gone through, I would just create a turbot so that they could see what types of data they're looking at. It'll be averaged at the end as well. So
Okay, is there maybe noise? You've got everything on a stand that may be vibrating at different frequencies because your slave passing frequencies are going to be different.
the board will be a little bit more mixed. It'll be external from all of the other stuff.
Okay,
That
so
way
it's not going to be
everything's going to be connected through wires. However, the board itself won't be directly.
it won't be on the stand.
It'll be
So on the outside of the stand, we're assembling a shelf, but it'll be separated from the actual test stand. It'll be connected, but it won't be inside the test stand.
But so if the test stand's vibrating, that's vibrating.
Yes.
How are you connecting the wires?
I was going to use a breadboard since it's not that much instrumentation. Plus, if I wanted to add any extra components, that would be a better way to do it. I'm using something like resistor or small transistor for amplification. However, I can also do PCB layout, so that's another option I'm looking into. However, right now I'd rather use the breadboard.
Well, yeah, so initially, but if you're going to expect someone like me to use this, the wires are going to come out of the breadboard in no time. And that becomes real difficult. You can keep dealing with it. So the breadboard is great for the preliminary stuff, but when you get to the point where you want this thing to be used by someone who is not an electronics aficionado, to keep the instrumentation working, something a little bit more, a lot more durable and consistent would be good. I need to be shielded. I don't know. That's the problem with stuff. Not getting this very good. Thank you.
Based on last year, you're gonna wanna use something that's a lot more sturdy for the connection, because stuff's gonna get on accident, or on purpose, I don't know either